Hello everyone, this is ECC3013 group project presentation. The topic of our group is digital filter. These are our group members. My name is Chen Mingyuan, my matric number is 209426.
And my name is Pradeep Nair. My matrix number is 207478.
Okay, next I will introduce the objectives of our group project. Number one, to apply the technology in mathematics course in analyzing Butterworth filter. To analyze the theoretically of the Butterworth filter. Number three, to perform the working principle of the Butterworth filter. Okay, what is the digital filter? In signal processing, a digital filter is a system that performs a mathematical operation on a simple, discrete time signal to reduce or enhance certain aspects of that signal. This is in contrast to the other major type of the ecological filter. The analog filter, which is typically an electronic which is typically an electronic circuit operating on continuous time log signals. Okay, what is finite impulse response filters and infinite impulse response filters? Number one, IR is the infinite and used for applications where linear characteristics are not of the cursor. Number two, IR is better for low order typing, whereas the FIR factor is used for higher order typing. Number three, IR factors are recursive and used as an alternative, whereas FIR factor has become too long and cause problems in various applications. Okay, I will introduce the Butterworth filter. The Butterworth filter is a type of a signal processing filter designed to have a frequency response that is as light as possible in the passband. It's also referred to as a maximally flat magnitude filter. It was first described in 1930 by the British engineer and physicist Stephen Butterworth. Butterworth filters are called maximally flat filter. The two-pole filter was a damping ratio of 0.707. It's the second oscillator. Butterworth filters are used in the control system because they don't have picking. Low pass filter and the high pass filter. Low pass filter is a type of the frequency and the domain filter that is used for smoothing the image. It attenuates the high frequency component and favors the low frequency component. A high pass filter is a type of the frequency domain filter that is used for sharpening the image. It attenuates the low frequency components and preserves the high frequency components. Okay, low pass Butterworth filter. The low pass Butterworth filter is an active low pass filter as it consists of the op amp. This op amp operates on the non-inverting model. Hence, the gain of the filter will decide by the resistor R1 and RF, and the cutoff frequency decided by R and C. Okay, next let my partner to introduce.
Okay, as for the next part, I'll be talking about the working principle of Butterworth filter. First and foremost, we have to understand the working principle of Butterworth filter. So what is meant by this is when it is in transition medium at the cost of steepness from passband to stopband, the Butterworth filter will dispense a flat response where the output signal is concerned. Okay, next. Okay, The following formula illustrates to us on how to calculate the amplitude response of the nth order Butterworth filter. So as you can see here, the formula is V out over V in equal to 1 over square root in bracket 1 plus in bracket F over FC to the power of 2n. So n stands for the operating frequency of the circuit, and also F, no, wait, and the number of poles in the circuit is represented by n. The operating frequency of the circuit is denoted by F, and the center frequency of the circuit is symbolized by FC. Next, I'll be talking about the characteristics of the Butterworth filter. Um, Amplitude response, which is monotonic when it comes to both pass band and stop band. It is also around the cutoff frequency where you can observe quick roll off, which gets better with increasing order. Next, overshoot, which is considerable and ringing in step response, which gets worse with increasing order. Also, phase response, which is slightly non-linear in nature. And finally, largely frequency dependent group delay. Okay. As you can see here, I'll be discussing about Butterworth approximations right now. As we have understood previously, we must have higher order filters if we are to meet the specifications of the filter responses and achieve approximations which are near the ideal filter. Thus, the complexity of the filter will increase. Okay, next. For the next part, I'll be talking about the method. The method of signal filtering by Butterworth filter is the digital signal which is processed by a digital computer, and the processing is calculated in accordance with a pre-programmed program. At its core, it is a digital signal processor. The so-called digital filter is to transform the input sequence into the output sequence through certain operations. As shown in the next slide, the time domain input relation is yn hn, it's times by xn. Okay. If the Fourier transform xn and yn exists, then the frequency domain relation of input and output is, as you can see from the diagram here, it says y e to the power of jw minus x e to the power of jw times with h e to the power of jw. So you can see here from what you can observe here, xn is the input and the process is hn, and then the output will be yn. Next. Okay. For the subsequent part, I'll be talking about logarithmic frequency scale. On the frequency scale, a decade is a tenfold increase, which is defined by multiplying by 10, or tenfold decrease, which is understood as dividing by 10. An octave is a doubling, which is multiplied by 2, or halving, which denotes dividing by 2 of the frequency scale. As with the first and second order filters, the third and fourth order high pass filters are formed by simply interchanging the positions of the frequency, determining the components, resistors, and capacitors in their equivalent. Yeah. The Z transfer function for the Butterworth filter, I'll be talking about this right now. The relationship between the Laplace transform and the Z transform is Z is equal to E to the E square ST, E to the power of ST, sorry, where T is the sampling time. For example, T equal to 1 over Fs, and Fs denotes the sampling frequency. Thus, according to this formula, S is equal to 1 over T ln Z, which is approximately about 2 over T times with Z minus 1 over Z plus 1. Okay. Right now, as you can see, I'll be talking about Butterworth filter design using Cower topology. The Butterworth filter can be realized using passive components such as series inductors and shunt capacitors with Cower topology. Cower one form is as shown as below in the diagram. So you can see the diagram over here. Yeah, you can see the filter diagram over here. Okay. So for the next part, this is Butterworth filter design concerning the use of silent key topology. The Butterworth filter, which is also linear analog filter, can be realized using passive components and active components such as resistors, capacitors, and operational amplifiers using Sallen key topology. So you can see the circuit diagram for Sallen key topology over here. Okay. The conjugate pair of poles can be implemented using each Sallen key stage, and to implement the overall filter, we must cascade all stages in series. In the case of a rail pole, to implement it separately as an RC circuit, the active okay. Next bro. Next one. Okay. So for this part, I'll be talking about application of Butterworth filter. The Butterworth filter is typically used in data converter applications as an anti-aliasing filter because of its maximum flat passband nature. The radar target track display can be designed using Butterworth filter. The Butterworth filters are also frequently used in high-quality audio applications. In the motion analysis, digital Butterworth filters are used. Okay. Right now, I'll be talking about normalized low-pass Butterworth filter polynomials. To help in the design of his low-pass filters, the scientist and engineer himself, Mr. Butterworth, produced standard tables of normalized second-order low-pass polynomials given the values of coefficient that correspond to a cutoff corner frequency of 1 radian per second. So in this slide, you can see the table over here. So I think you can refer to the table to understand what I'm trying to explain over here. So next slide. So we have come to the conclusion of this report. First and foremost, I would like to, on the behalf of my group members and we would like to thank Dr. Fuza for her guidance throughout the duration of this report. Without whose invaluable guidance, we couldn't have completed it on time. Also, we would like to note that we were able to work together as a team and we learned the value of teamwork. And as for what we have learned as well, we learned regarding Butterworth filter design. We learned about ideal frequency response for Butterworth filter, low pass filter and high pass filter characteristics. And we talked more about in depth regarding low pass Butterworth filter, and also we learn about how to design windows, and we understood the working principle of Butterworth filter. We were able to learn about Butterworth approximations. Then we were able to learn about the method that is used to design a Butterworth filter. Then we were also exposed to the logarithmic frequency scale, and we gained knowledge on the Z transform transfer function for the Butterworth filter. And we also learn more in depth about Butterworth filter design using Tau topology and Sallen key topology. At the same time, we were able to understand about the digital implementation, and we were also able to learn regarding the application of Butterworth filter together with normalized low-pass Butterworth filter polynomials. That is all from us. Thank you very much.
Thank you, Aruna.
Okay, right.